Okay, let's go ahead and get started. So, I have just a couple of announcements. So the midterm is next Thursday, evening, and it'll be in the same room as it has been the last two times. So I'll, post that. I don't know the room number off the top of my head, but I'll, recall what it is and post it. And then also for the second half of class today, there's gonna be a visitor, so just ignore him. He'll probably just enter in, and he's just visiting the math department and wanted to see a calculus class, and so yeah, he'll be here for like the second half of class. Okay, so this week we've been looking at the integral. So the definite integral looks something like this. So this is the thing that computes, if f is positive, then it computes the area under f from a to b, and if it's positive and negative, it'll just subtract off any areas that are below the x-axis. So this is something like a signed area between the curve and the x-axis. So just to draw a picture, if the curve looks something like that, and this is, say this is A and this is B, then the integral will add this blue area and subtract this pink area and give you the total. Yeah.
So there's the same principle of multiplying two negatives by each other over here. So suppose like it's like A to B, but A is to the right of B, and then also the area x-axis.
Yeah.
Would that net out to a positive area, but it's like backwards?
Yes. Yeah. Yeah, so yeah, we saw a few properties of the integral last time. So one of them being if you flip A and B, then that puts a minus sign in front of and we saw a few other properties, and these will be helpful in calculating integrals. So what we're gonna do today is introduce another function. So right now the integral is just a number, right? Like you give it a, b, and an f, and it will just tell you what the area under the curve is. So what we're gonna do in a second is I'm gonna allow b to vary, and so that will give us a function that depends on. And what we'll be able to do with that is we'll actually be able to compute integrals more easily, because we'll be able to I don't want to spoil the answer, but we'll be able to use that function to relate back to other techniques that we've been using this semester. So let me introduce that thing. It's called the accumulation function. So I'm going to let f be integrable on the interval from a to b. Then the accumulation function which I'll call capital F, is the following thing. So if I give it an input x, then what it does is it computes the integral from a to that input x of f of t dt. Okay, so let me draw a picture to break this down. So let's say this is the graph of f, and let's say this is a, and this is x. So okay, ignoring this for now, we know that the integral from a to x of f of t dt is just going to be this area. right? So I'll just shade this in. So now what we're doing is we're allowing X to vary. And so you can imagine taking this vertical line and just dragging it, and the area gets larger or smaller depending on where you drag it. So we might drag this along. So this value X will vary from A to B. Let me put a B in here. And the function capital F, this accumulation function, will just report what is the area of this pink region for one of those values of X. Okay, so let me just write down a few of those points. So X varies from A to B. And for any fixed X, then this is one number. Right, so going back to like day one, what is a function? I give it an input and it gives an output. So here my input is X. And then the output is whatever this area is. So this tells me that as X varies, so does the value of this integral. And so that means that F of X is a function of that variable X. Is this making sense? We're going to compute a couple of examples. Further questions? Okay, so let's compute the first two easiest examples. So what if little f is a constant, and also what if little f is linear? So let's start with the constant one. So let's let little f of t. So I'm going to use t to make it not confusing with x, which is the variable for capital F of x. So I'm going to let f of t just be some constant. Okay, so let me draw a picture for this. So here's my constant c. And then I'm going to look at, so I'm going to let capital F be the accumulation function starting at, so going back, I need to pick an A. So I need to fix an A. So I'll take f of x to be the integral from 0 to x of f of t dt, which is just c dt. Okay, so we're starting at 0, and then for a particular value x, where this integral is going to tell me the area of this rectangle. So that we can figure out, right? Because this rectangle just has base. So what is the size of the base? Yeah, it'll depend on x, right? Because like as I move x around, that base will get wider or smaller. So the width of the base of the pink rectangle is x. And then what is the height of the rectangle? Yeah, so then the height is just c. So then how do we simplify this? What is f of x in this case? Yeah, so it'll just be cx because it's just calculating the area of this rectangle. Okay, so that's sort of our first example. Are there questions about this? Yeah.
Question about the coverage for the midterm, but I'll have my focus.
It'll be up through the end of Wednesday. Yeah, so this won't be on the midterm.
Wait, this coming.
No, the stuff that we've already done up until 10 a.m. this morning. Yeah, so this, whatever we're talking about today won't be on there. Okay, so are there other questions about the example? Sounds good. So let's do another example. So I'm going to let now f of t equal t. And I'll also start at 0 again. So f of x will be the integral from 0 to x of t dt. Okay, so let's draw a picture again. So here is the graph of little f, which is just t. And then here's 0. And then if this is x, then I'm calculating the area of this pink triangle. Okay, so take like 60 seconds to think about what the area of this triangle should be. Okay, so what's the area of the triangle? Yeah. So, okay, yeah, so so you said 1/2 t. Yeah, so we're plugging in x, right? So it'll be 1/2 base times height. The base is x, and then the height will also be x, right? Because that's what f of t evaluated at x is. So this is 1/2 base times height, which is x squared. That's what we get there. Okay, so let me summarize our two examples. Okay, so in the first example, we had little f of x was a constant and capital F of x was cx. And in the second example, we had little f of x is equal to x and capital F of x is equal to 1/2 x squared. Okay. Do you notice anything about any kind of pattern emerging or something about the relationship between little f and big F? Yeah, what is it? Yeah, so if you take the derivative of this one, you get this one, right? So for power rule, we would multiply this by 2, so this would go away and we'd just be left with x. And then same thing here, if you take the derivative of this, you're just left with the constant. So in other words, capital F is an antiderivative for little f. So this is our guess based on these two examples, that capital F prime of x is equal to f of x. Okay, so let's take a minute to think through why this might be the case. So I think just doing these two examples, it's not very illuminating, like why you would get, why when you take the derivative of this, you would get this one. So let me give you some intuition for why this might be true. Okay, so let's just assume for the moment that f of x is greater than or equal to 0, so that this integral is just an area. So that this accumulation function is an area. Okay, so what we want to do is compute the derivative of this and check to see whether or not we got that back. So we don't have any derivative rules yet for dealing with the integral, so we're going to have to go back to the definition of the derivative as like a limit of slopes. So what we want to do is compute f prime of x from the definition. So this is going to be the limit as h approaches 0 of f of x plus h minus f of x divided by h. So this is f prime of x. Okay, let's figure out just what this numerator is, because this term f of x plus h is an area, and this is also an area, so maybe this expression is also giving us the area of some shape. So okay, so here's my function little f, and let's say here's x, and here's x plus h, and I'll just put a over here at the y-axis. Okay, so f of x plus h, so I'll circle this in pink, that is the area of this region, right? And then the area described by f of x, capital F of x, so I'll do that in blue. So that is this area. Okay, so what the numerator of this limit is pink minus blue, right? So I'm just left with this region on the right. So the pink minus blue gives the yellow region. Does that make sense? If I take that whole area and subtract out the blue area, then I'm left with at least this area. Okay, so how can I write an integral that describes the yellow area? Yeah.
Would be like integral of x to x plus h.
Yeah, exactly. Yeah. So this just changes like the bounds of integration. So we get that this yellow thing is described by the integral from x to x plus h of f of t dt. Okay, so what's happening here is we're taking the limit as h goes to 0, right? So h is going to get really, really small. And this is going to start to look like just a sliver. So as h goes to 0, so here we have x, maybe here's x plus h. So the yellow region looks something like that. So this is starting to look like a rectangle. As h gets smaller and smaller, it'll be a rectangle with base h and height equal to f of x. So So notice as h approaches 0, this starts to look like a rectangle with base h and height f of x. Okay, so to write that as an equation, so recall this yellow rectangle was describing this difference in the numerator. So we get that f of x plus h minus f of x is approximately equal to the area of this rectangle, which is h times f of x. So far this is just the intuition. This is like the fuzzy version, but does this approximation make sense? I'm happy with this. Okay, so I'm going to rearrange this. So if I divide both sides by h, then I get f of x plus h minus f of x divided by h is approximately equal to f of x. And this expression was exactly the thing that we were taking the limit of, right? So going back to the beginning, we wanted to figure out capital F prime of x, and so we were taking the limit of this. So this f prime of x, which is equal to the limit as h approaches 0 of x, f of x plus h minus f of x divided by h. So we're thinking this should approximately be the limit as h approaches 0 of f of x. But of course, this doesn't depend in any way on h, so this is just f of x. Okay, so this is sort of the intuition behind why our guess about what's going on might have been true. Are there questions about this? Okay, so let me state the theorem. And this is called the fundamental theorem of calculus. And there's two parts to this theorem. So this is part 1, and we'll get the sequel on Monday. So here's part 1. So let's say f is continuous on the interval from a to b. Then what this says is that the accumulation function capital F of x, which is defined as the integral from a to x of f of t dt. So as x goes between a and b. So what this theorem says is that this thing is, first of all, it's continuous on the interval from a to b. It's also differentiable. And furthermore, its derivative is what we thought it was. It's equal to x. So let me write all that down. So, so this is continuous on a to b. It's differentiable. on a to b and capital F prime of x is equal to f of x. Okay, so that's the statement of the theorem. Are there questions? Yeah.
Do you elaborate on why you call the
Yeah.
um,
So you can think of it as just like accumulating area under the curve, if you like. Yeah. Yeah, so that's sort of where the name comes from. Yeah. Are there other questions? Okay, so let me rephrase what this theorem is saying. So another way that you could think about this is that this capital F of x is an antiderivative for little f of x. So last week we were working in finding antiderivatives and basically just undoing the process of differentiation to figure out what the possible antiderivatives for a function could be. And what this is saying is that our capital F of x, the accumulation function, is an antiderivative. But more than that, it's also I'll pause there and I'll do some examples. So here's like two ways that you might use this theorem. So two first examples. So one example is now we can take the derivative of functions that are defined in terms of integrals. So for example, you might wonder, what is the derivative of something that looks like this? The integral from 0 to x of the square root of t squared plus 1 dt. So this is really easy. All it is it's just the inside function, right? That's what the theorem tells us. This is okay, so that's one quick consequence of the theorem, is that now we can take the derivative of functions defined using integrals. Here's another one. So let me show you another example. So what if we want to know actually what is a function defined using an integral in terms of like more simpler everyday functions? Yeah.
He's like, you're saying like, what is the derivative of, but then it's like, like, you're saying, like, capital F of x is the integral, right, not the derivative, so I'm just confused about that.
Yeah. Okay, this is confusing. So capital F of x is a function that's defined using an integral, and the x is getting plugged in as the upper bound of the integral. So like the picture you can have in your head is like, this is calculating some area under that curve, square root of t squared plus 1, and we're like dragging the right endpoint of the shape. And then, so that's the function. I give it a specific x value, and it spits out an area of some shape. And whenever we have a function, so the theorem says it's differentiable, we might wonder what the derivative is. Yeah. Does that address your question?
Yeah.
Yeah. I think sometimes like there's a lot of variables floating around, and so sometimes it's like it gets a little bit confusing, but it helps to just take a step back and sort of think about like, what is this function actually doing? Okay, so here's the second example. So what is, that's my laser, the integral from 0 to x of cosine of t dt. Okay, so the theorem will help us write this in a much simpler form. And here's how we can do that. So last week, I might have asked you a question like, what is the antiderivative of cosine of x with, so maybe I'll call this f of x, with some initial condition, right? So let's say f of 0 is equal to 0. Okay, so how we approached these problems was find the general antiderivative and then use this initial condition to solve for what the plus c has to be, right? So what is the general antiderivative? Yeah, so it's going to be sine x plus c. And then if I want f of 0 to be 0, what should c be? 0. Yeah, so this will also be 0. So I get f of x is equal to sine x. Okay, so now that we have the answer, let me convince you this is the same question. So the theorem tells me that whatever this function is, this is going to be an antiderivative of cosine. Okay, so then the question is which one? We have to figure out what c has to be. But we know that if I plug in x equal to the left endpoint of the interval, that's calculating the area of a region that doesn't exist, right? It's just a sliver. So that area will be 0. So that tells me that whatever this function is, it's an antiderivative of cosine, and it's the one where if I plug in x equals 0, I get 0. Does this make sense? Okay, so this is like another way that the theorem is used, and I just wanted to show you this example now, but you'll get a lot more practice with this type of problem as we go on. Yeah, do you have a question?
Yeah, so these are supposed to be like indefinite integrals versus like having actual number of values for the x.
So we're, yeah, the territory, we're getting into murky waters, right? So at the moment, this is still a definite integral, right? Because I'm plugging in 0 as the left point and x is the right endpoint. And x is just a number, but it's allowed to vary.
Okay.
Yeah. Yeah, we'll be getting into that. Yeah, no, there's nothing. So if it's A to B, that's a definite integral because you have like specific bounds for the integral. Okay, so where are we? Okay, so I'm gonna prove this fundamental theorem for you. So the intuition that we saw earlier is roughly how the proof goes. So let's take a look at the proof. Okay, so we know, so we want to take the derivative of the accumulation function. So we know f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. Okay, and earlier, we also said that this thing, f of x plus h minus f of x, let me just scroll back to the picture. So here, we drew a picture of what, so f of x plus h, this pink thing, was the pink area, and we subtracted off the blue area, and we got this integral. Okay, so we know that this is equal to the limit as h approaches 0 of 1 over h, and then I'm just replacing the pink box with the thing we calculated earlier. So this is the integral from x to x plus h f of t dt. Okay, are we comfortable so far? Okay, so this is the limit of a scary function. So whenever we're taking the limit of something scary, the easiest thing to do is to squeeze theorem it in between two really easy things, right? So that's what the approach that we'll take here. So our goal is going to be to squeeze this in between two simple things. Okay, and the easiest thing that we could squeeze it in between is constants. So let's just do the easiest thing we can think of and just say, what is the maximum value of f on our interval, and what is the minimum value of f on the interval? And then argue that this integral has to be in between two just numbers. So let's look at this. So let's let capital M be the maximum of f on the interval from x to x plus h. Okay, so h is going to be shrinking, so whatever this number m is might depend a little bit on h. But for now, let's just write m to be the maximum. And let's let m, little m, be the minimum. Okay, so by the way, we had a theorem called the extreme value theorem that told us a continuous function on a closed interval has a maximum and a minimum value. So that's why we're allowed to do this. This exists by the extreme value theorem. Okay, so we know that f is going to be in between those two values on this on the interval. Okay, so I'm going to do something sketchy and then let's justify it. So what I'm going to do is I'm just going to hit everything in the sequence of inequality with an integral. So I'll just integrate everybody from x to x plus h. Oops. Oh, and this should be dt. Okay, why is this okay? Yeah, so, okay, that is true, but if I multiply everything by -1, all the inequalities would turn around, right? So, okay, so let's think about like why, let me get a chalk. So, let's just look at one inequality. So here I have like a little function and then a bigger function. So here's my little m, and then f of t is something sitting above it. So the integral, let's say from x to x plus t. Say what? Oh, you're right, they do need to touch somewhere. Okay, so, okay, now they touch. So the integral, let's say this is 0 also. The integral of m is just going to be this small box. And the integral of f will be the small box plus this area that's under f but above m, right? And then again, if I had capital M, that area is an even bigger rectangle. Oh, and it has to touch. Okay. Okay, so do we find the inequality believable? Okay, so the good news about this is we know how to calculate this, right? So what is that? So it's the area of a rectangle, and the rectangle has base, oops, and there should be h. Base h and height m. Right, so this is just going to be mh less than or equal to stuff. And then the big rectangle will be capital MH. Okay, as h gets smaller, as that interval shrinks, what happens to little m and big M? Is it possible that they're both different numbers as h goes to 0? Oh, yeah. No. It's actually not possible. Okay, so maybe it would be if my function wasn't continuous, right? So if f had like a jump discontinuity, then like little m might always be down here and big M is up here, and I start squeezing these numbers together and they disagree. But if f is continuous, it's going to force little m and big M together. Do you guys believe that? Okay, so as h approaches 0, little m and big M approach one another. So let me divide through this inequality by h. So we get m less than or equal to 1 over h of this integral. Less than or equal to m. And then when I hit all of this with a limit, so if I take the limit as h approaches 0, m Okay, since these two numbers are going to approach the same value, by the way, what is the value of that number? Yeah, so it has to be f of x. I get by the squeeze theorem that this whole thing, which was equal to f prime of x, has to equal f of x. Okay, so let me just recap for a second. So the squeeze theorem and these inequalities force this limit to equal f of x. And we had previously argued that this limit was equal to f prime of x. So we get the conclusion of the theorem. Okay, so in my opinion, this theorem is worth celebrating. And the best way to celebrate is with cake. So, so I have a cake. Yeah, class is over and you guys can come up and get